Next question. Can you explain what a deadlock is and walk me through how you would solve it if you encountered a deadlock in production? Let's go through the answer. A deadlock is a situation where two or more threads are permanently blocked because each one is waiting for a resource that another thread is holding and neither ever releases what resource one has. The application freezes, no progress is made. The classic scenario is this: thread A acquires lock 1, then tries to acquire lock 2. At the same time, thread B already has acquired lock 2 and then tries to acquire lock 1. Thread A is waiting for thread B to release lock 2 and thread B is waiting for thread A to release lock 1. Neither will ever move forward. That is a deadlock. Now, if I encountered this in production, this is how I would approach it. First, I would diagnose the situation. In Java, I would take a thread dump, either using JStack on the running process or through a tool like Visual VM or Java Mission Control. A thread dump shows the state of every thread and what locks each one is holding and waiting for. A deadlock shows up immediately as a circular chain: thread A waiting on thread B and thread B is waiting on thread A. It is like a cycle. Once confirmed, my immediate fix in production is to restart the affected service to restore availability. But that is just buying time. The real work is fixing the root cause so it never happens again. For the permanent fix, the most reliable approach is lock ordering. I would establish a global rule that locks must always be acquired in the same fixed order across all threads. If every thread acquires lock 1 before lock 2, a circular wait can never form and deadlock becomes structurally impossible. I would also consider replacing raw synchronized blocks with reentrant lock and its try lock method, which lets you attempt to acquire a lock without a timeout, not without a timeout, but with a timeout. If the lock is not available within that time, the thread releases everything that it holds, backs off, and retries. This breaks out of a deadlock automatically, even if one forms. Next question. Imagine two threads in your Java application are both frozen and not making progress. How would you diagnose and fix this? If two threads are frozen and not making any progress, my first suspicion is a deadlock. But I would not assume that immediately. I would diagnose it first. The first thing, as I would have done in the first case, is take a thread dump. In Java, I run JStack against the process ID of the running application or service. This gives me a snapshot of every thread, what state it is in, what it is doing, and critically what locks it is holding and what locks it is waiting to acquire. If it is a deadlock, the thread dump will tell me directly. Java's JVM actually detects circular lock dependencies and flags them explicitly in the output. I would see something like thread A is waiting for thread B and thread B is waiting for a lock held by thread A. That confirms it. If the thread dump does not show a deadlock, I would look for other causes. The threads might be in a live lock where they are both actively running but constantly reacting to each other and making no real progress. Or they might be starving, where a low priority thread never gets CPU time because high priority threads keep taking over. Once I confirm whether it is a deadlock, I handle it in two stages. Immediately, I restart the service or kill and restart the frozen threads to restore the application to a working state. In production, availability comes first. Then permanently I go into the code and find where the two locks are being acquired. The fix is lock ordering. I enforce a global rule that lock 1 must always be acquired before lock 2 everywhere in the code base. This makes circular wait structurally impossible. I would also refactor the locking mechanism. Raw synchronized blocks give you no escape hatch. a thread waits forever, I would replace the synchronized blocks with re-entrant lock and use try lock with a timeout, so that if a thread cannot acquire a lock within a set time, it releases what it holds, waits briefly and retries. This gives the system a way to recover automatically even if a deadlock forms. Finally, I would add monitoring going forward, thread pool metrics, lock contention alerts, so that if this pattern starts forming again, I catch it before it freezes the application. Next question: what are the conditions required for a deadlock to occur, and how would you prevent it at the design level? For a deadlock to occur, four conditions must all be true at the same time. Computer scientists call these the Kaufman conditions for deadlocks. The important thing is, if you eliminate even one of them, a deadlock cannot form. The first condition is mutual exclusion. Only one thread can hold a resource at a time. If two threads could share a resource freely and simultaneously, there would be nothing to wait for. The second condition is hold and wait. A thread is already holding at least one resource and it is waiting to acquire another one without releasing what it already has. The third condition is no preemption. The system cannot forcibly take a resource away from a thread. The thread must release it voluntarily. If the system could just take locks away, it could break any deadlock instantly. The fourth condition is circular wait. There is a circular chain of threads. Thread A is waiting for something, thread B holds. Thread B is waiting for something, thread C holds. Thread C is waiting for something, thread A holds. The chain loops back on itself. All four must be present continuously. Remove any one and deadlock is impossible. To reiterate, the conditions are mutual exclusion, holding and waiting, no preemption, and circular wait. These are the four conditions that cause the deadlocks to occur, and these are called as Kaufman conditions. Now, how do I prevent the Kaufman conditions or one of these conditions at the design level? The most practical prevention is eliminating circular weight through lock ordering. I define a global order for all locks in the system and enforce that every thread acquires locks in that particular order always. If every thread takes lock 1 before lock 2, a circular chain can never form. This is simple, reliable, and costs nothing at runtime. This is called lock ordering. The second approach is eliminating hold and wait. I design threads to acquire all the locks they need at once upfront before doing any work rather than acquiring them one at a time as they go. If a thread cannot get all the locks it needs immediately, it acquires none of them and tries again later. This prevents the situation where a thread is holding something while waiting for something else. The third approach is allowing preemption through timeouts. I use reentrant lock with try lock and a timeout instead of raw synchronized. If a thread cannot acquire a lock within the timeout period, it releases everything it holds and backs off. This effectively introduces a form of preemption at the application level, even though the JVM itself does not support it natively. The fourth and most powerful approach is eliminating shared mutable states together. If threads do not share resources that can be locked, deadlock cannot occur by definition. If I achieve this through immutable data structures, data that cannot be modified after creation, so any thread can read it without a lock, or through message passing, where threads communicate by sending messages to each other rather than accessing shared memory directly. This is the design philosophy behind languages such as Erlang and frameworks like Akka in Java. In practice, at the design level, I also keep critical sections, the code inside locks, as short as possible. The longer a thread holds a lock, the higher the chance of contention. And I avoid calling external methods or input output operations while holding a lock, because those can block unpredictably and dramatically increase the window for deadlock to form. So in short, deadlock needs all four Kaufman conditions. Okay, and the four conditions are exclusion, hold and wait, no preemption, and circular wait. And the way to avoid this is eliminating the circular weight through lock ordering, and eliminating hold and weight so that the threads can acquire all the locks they need at once. The third approach is allowing preemption through timeouts by using reentrant lock with try lock and a timeout instead of raw synchronized. The fourth one is sharing mutable state altogether. That is, the threads share resources that are immutable data structures, data that cannot be modified after creation. So, deadlock at the design level, the most reliable prevention is lock ordering to eliminate circular weight combined with minimizing shared mutable state wherever the architecture allows it. I'll see you in the next audio.